So in case of those of you who teach reinforced concrete, you will probably know the bond strength is developed by 4 mechanisms actually. The pull-out strength is based on because of the ribs. So you have the concrete surrounding the ribs, so that will put the that will confine the concrete, and there is frictional resistance on the surface, and there is failure along the outer edge of the ribs. So these are 4 different mechanisms for load transfer between bars and the concrete. Okay. Whereas in case of reinforcing FRP bars, on this we don't have ribs, right? On this we have ribs, but at the same time these ribs are not as efficient as the steel ribs. These can, they can actually shear off. These ribs can actually shear off, and these are based on spiral fiber, which will give a better bond for sure. But in some cases, some of the producers, they machined grooves. That is even worse. It won't really help in any way. So bond is going to be a problem. And in case of FRP, primary mechanism for load transfer is either chemical bond at the interface or some small amount of frictional resistance. That's all. That's the reason you will see the bond is likely to govern your design. And I'm giving out all my secrets, so pay attention here. The lack of bond will prevent you from using higher stresses in FRP bar. The FRP bar may have like 800 MPa strength, but the bond will limit it to 150, maybe, or even 175 or 200. So really we are limited by the bond, therefore you cannot use the higher strength. Does it make sense? So you have to, we have to check that. I will show you how to check that. We will do that later. So number one, if we have a larger modulus or higher modulus material, that's very helpful for FRP bars. The second helpful thing is bond. If you are increasing the bond significantly, that will definitely help your cause. Okay. And in case of FRP bars, stronger the surrounding concrete, it won't make any difference to the bond strength. Whereas in case of steel reinforced concrete, that will give you better confinement around the ribs, and that's the reason you'll get a better bond strength with higher grade concretes. Whereas with FRP bars, it doesn't make any difference. And the manufacturer should give you the guaranteed strength and stuff like that. So it's already 1:40, right? I have about 7-8 slides. Should I go over this or should we stop here? Completed? Okay. I'll go a bit faster, we'll be done. So creep rupture strength, we'll come back to this again when we are actually designing it. But for now, just remember that creep rupture strength is likely to be governing your design later. Fatigue properties, one of our students, he talked about fatigue. He's working on fatigue properties. Fatigue properties are indirectly checked in this document. There is no direct checking of fatigue strength. So again, we'll talk about it when we are dealing with fatigue design. High temperature and fire it's not a very good material for high temperature and exposed elements. Durability. So again, tensile strength and bond strength are more important in FRP reinforced concrete. Durability is still very, very gray area. What I mean by gray area is we don't know much about durability. So if some of you would like to do some research, durability is a good topic to pick up your or to do some research on FRP related materials. It's a good thing to do. but you may not like the results. I'm sorry, because we have already done that. So I know that the results are not very attractive to the manufacturers. So they don't want to give you money when they know that it's not going to give them good results. So that's a problem. But it is what it is. So we publish our work, let them look at it, do whatever. It doesn't matter. To me personally, it doesn't matter. So durability is an issue that one should consider, because you'll have a lot of problems with alkali exposure to alkali environment. Test result. Again, the other problem is all these durability tests ideally should be performed over many months or even years, right? Like 5 years, 10 years. But you want instantaneous results. I want results now, right? The guy will come, I'll write a check, no problem. I want your results tomorrow. How do I do that? You cannot do it. So you find ways to correlate accelerated tests with actual normal exposure tests. Very difficult. How do we correlate these two? Same problem with corrosion. Many of us, we do a lot of accelerated tests and corrosion tests, but people turn around and say, okay, but how do I relate actual durability over 100 years to the accelerated test that you are doing right now over just less than 3 months tests? That's the problem. So that's another thing that if you like to do research, that's one area which is a good area to work on. Okay, now there is a strength and modulus grades. I will jump to the next slide and I will tell you what it is. Okay, maybe this, yeah. See, we have a bar identification symbol in ACI. So here we have 3 letters here, dash, G for glass, C for carbon, and A for aramid. You can use those standard notations. Or you can use B for basalt, but basalt is not recognized in ACI yet. Then F80, F for tensile strength, guaranteed tensile strength. 80 is 80 KSI actually, and 80 KSI works out to be about 550 MPa in this case. So if you are specifying something like this, that F80 means 80 KSI tensile strength. E is modulus, 5.7 MSI, million cycles, million pounds per square inch. So 5.7 million pounds per square inch will give you 39.8 GPa in this case. So depending on your bar, you can change this. You can say E of 9, let's say, which is difficult to achieve, but if that's what you are specifying, the producer should give you guarantee that the material he is supplying will be 9 GPa modulus, will have 9 GPa modulus. So this is how you classify or identify your bars. And the last, this one here, it can be anything. It can be a special note. In this case, 0.75 means that extra identification tells you it's a it has outer diameter of 0.75 inch, 3/4 inch, 19.1 millimeter. So you can, in the industry, we don't want to be biased. So the ACI gives you general guidance, and as design engineers, you will specify the bars based on your calculations. You are not going to say you must buy your bar from Hugh Brothers. You cannot say that. You cannot say you must buy your bars from so and so or so and so. You cannot do that. So you give the properties, minimum properties, and they should match those properties. They should make sure those properties are achievable for their product. Only then you can use those products, right? So you don't want to include bias in your specification. So I'll go back to this. So this is what I already mentioned. Letter F followed by minimum tensile strength in KSI. And then letter E followed by modulus. So modulus in million pounds per square inch. So for example, if you have E10, that will mean you should have a modulus of at least 68.95. And then ACI also has a table which is similar to what they have in Hugh Brothers. In fact, it's the other way around. Hugh Brothers matched with ACI table, and they have similar physical properties, except that the tensile strength and modulus are based on their own product. So with that, we can finish for today, and we still have a quiz number 2. I think you got quiz number 2. We will send you the files. I'll send you 3 files. One with the slides, one with my notes for micromechanics, and the other one is the Excel spreadsheet. So if you want to use Excel spreadsheet, use it. If not, you can do hand calculations. You're more comfortable using hand calculations, so be it. It's all there, okay? So we'll see you tomorrow. Thank you.